The past feels solid, fixed, locked, untouchable. Whatever happened, already happened. Nothing you do right now should be able to change it. That's common sense, and it's completely wrong. There is an experiment in physics that suggests something deeply unsettling. A choice you make today can be linked to what a particle did in the distant past. Not metaphorically, not philosophically, physically, measured, tested, repeated, and it leads to a conclusion that sounds impossible the first time you hear it. The past might not exist until you look at it. Pause for a second. Because if that's true, then everything you believe about time begins to fall apart. We are taught that time flows in one direction. Cause comes first. Effect comes after. You drop a glass, it shatters. You don't see shattered glass and then decide to drop it. The arrow of time feels obvious, safe, reliable. But quantum mechanics doesn't care about what feels obvious. At the smallest scales of reality, particles don't follow the rules you expect. They don't behave like tiny solid objects moving through space. They behave like possibilities, clouds of probability. And sometimes those possibilities don't resolve until a question is asked. Not when the event happens, but when it is measured. That distinction is everything, because it suggests something deeply counterintuitive. Reality is not fully defined until it is observed. Now here's where things start to break. Imagine something happens, not just a moment ago, but billions of years ago, long before Earth even existed, long before you were here to observe anything. You would assume that event is already decided, written into the fabric of the universe, unchangeable. But what if that's not true? What if that event is still somehow open, waiting, not in the sense that it can be changed freely, but in the sense that it was never fully decided in the first place, and the only thing that completes it is a measurement made in the present. This is not science fiction. This is not a thought experiment disconnected from reality. This is based on real experiments that have been performed in laboratories. Experiments that show something deeply disturbing. The way you choose to observe a system now can determine how that system behaved before. As if the universe is not recording history, but generating it in real time, and sometimes filling in the past after the fact. If that sounds impossible, good. Because to understand this, you have to let go of one assumption, that the past is already finished, because in quantum physics it might not be. And to see why, we have to start with one of the strangest experiments ever performed, one that already breaks reality before we even make it worse. Now, to understand how this could even be possible, we have to start with an experiment that already breaks reality on its own. Imagine you have a device that fires tiny particles of light, not a beam, not a stream, one particle at a time. Each one completely isolated. You aim these particles at a barrier with two narrow openings, two slits. Behind that barrier is a screen. Every time a particle hits the screen, it leaves a tiny mark. So you start firing them, one by one, slowly, carefully, and you wait to see what pattern forms. Common sense tells you what should happen. Each particle should go through one slit or the other, so over time you should see two clusters forming on the screen, one behind each slit. Simple, predictable. But that's not what happens. Instead, something impossible appears. A pattern of alternating bright and dark bands, stripes, not two clusters, not random dots, a structured wave pattern. And this makes no sense, because you are firing particles one at a time. There is no second particle to interfere with, nothing for it to collide with. And yet, the pattern that forms is exactly what you would expect if waves were interfering with each other. As if each particle somehow passed through both slits at the same time, as if it split into possibilities and interfered with itself. Let that sink in. A single particle behaving like a wave, not choosing a path, not going left or right, but somehow exploring both. This is not a theory. This is one of the most well-tested experiments in physics, and it works every time. But it gets even stranger, because the moment you try to figure out what the particle is actually doing, everything changes. You place a detector near the slits, something that can tell you which path the particle takes, left or right. You run the experiment again, same setup, same particles, same screen, but now you are watching, and suddenly the pattern disappears. The interference is gone. The stripes vanish. And what replaces them is exactly what you expected from the beginning. Two simple clusters, as if each particle chose one path and stuck to it. It's no longer behaving like a wave. It's behaving like a solid object, a particle. So just by asking the question, which path did you take? You forced reality to change its behavior. Nothing else changed. Not the distance, not the setup, not the particles themselves. Only the information you chose to extract. And that changes the outcome completely. This is the moment where intuition breaks, because it suggests something deeply unsettling. The particle was not secretly a wave or secretly a particle all along. It wasn't hiding a fixed identity. It only became one when you forced it to answer a question. When you measured it, reality didn't reveal itself. It responded. And now the real question begins. If simply observing the path changes what the particle does, then when exactly does that decision happen? Does the particle decide at the slit? Does it decide when it hits the screen? Or does it decide at the moment you choose how to measure it? Because if that decision can be delayed, then something even stranger becomes possible. What you just saw is often called the observer effect. But that name is misleading, because it makes it sound like consciousness is doing something special, like the universe is reacting to you watching it. That's not what's happening. You don't need a human. You don't need awareness. You don't even need eyes. All you need is interaction, information. The moment something in the system is capable of recording which path the particle took, the interference disappears. Not because someone looked, but because the information exists. And that detail changes everything, because it means reality is not responding to observation, it is responding to information. Whether anyone reads that information or not doesn't matter. The universe already knows. And once that knowledge exists, the wave behavior is gone permanently. So this raises a deeper question. Before the measurement happens, what is the particle actually doing? Is it really going through both slits, or is it secretly choosing one path and we just don't know which one? This was the argument that physicists like Einstein tried to make. He believed the universe had definite properties, that particles always had a real position, a real path, even if we couldn't see it. He thought quantum mechanics was incomplete, that there were hidden variables behind the scenes, something determining the outcome in advance. But experiment after experiment kept showing the same thing. There is no hidden path waiting to be revealed. The act of measurement doesn't uncover reality. It defines it. Before you measure, the particle is not in one place. It is not in both places in a classical sense either. It exists as a spread of possibilities, a probability distribution. And only when you ask a question does it give you an answer, not before. This is where things become difficult to accept, because it goes against everything your brain expects reality to be. We are used to thinking that objects exist independently, that they have properties whether we check them or not. A chair is in the room whether you look at it or not. A planet is orbiting its star whether anyone observes it or not. But at the quantum level, that assumption breaks. Properties are not fixed attributes. They are outcomes of interactions, of measurements, which means that what something is depends on how you choose to observe it, not in a vague philosophical way, in a precise, testable, physical way. And now we are ready to ask the dangerous question, because so far everything still follows a kind of timeline. The particle reaches the slits, then you measure it, then it behaves accordingly, cause first, effect after. But what if we change that order? What if the particle goes through the slits, and only later do we decide how to measure it? Not before, after. After it has already passed the point where it should have decided what it is, a wave or a particle. What happens then? Does it lock in its behavior at the slit and ignore what we do later? Or does something even stranger happen? Because if the outcome still depends on how we measure, even when that choice is made in the future, then the timeline you trust is no longer real, and the line between past and present begins to disappear. Up to this point, everything still feels strange, but manageable. You fire a particle, you choose how to measure it, and the result follows that choice. Cause, then effect. Even if the behavior is weird, the order still makes sense. The particle reaches the slits, then you measure, then reality responds. But now we're going to break that order completely. Imagine you let the particle pass through the slits first. No detectors, no measurement, nothing watching it. At that moment, based on everything we've seen, it should behave like a wave. It should go through both slits, interfere with itself, spread out as a pattern of possibilities. And then, only after it has already passed the slits, you decide what kind of experiment you want to run. Not before, after. You wait until the moment where the particle should have already chosen what it is. And only then do you ask the question. Do you want to know which path it took, or do you want to see interference? That choice is delayed. This is called the delayed choice experiment. And it asks something that sounds almost absurd. Can a decision made in the present affect what already happened in the past? Because think about what you are doing here. The particle has already crossed the most important point in the experiment, the slits. If it behaved like a particle, it went through one. If it behaved like a wave, it went through both. That moment is gone. It's already in the past. So whatever it did should already be fixed, independent of anything you decide later. But quantum mechanics refuses to follow that logic, because when physicists actually set up experiments like this, they found something deeply unsettling. The outcome still depends on how you choose to measure, even if that choice happens after the particle has passed the slits. Let that sink in. The behavior is not decided at the slits. It's not locked in when the particle moves through space. It's only resolved when the measurement is made, which means the question you ask later is somehow connected to what the particle did earlier. And this is where intuition starts to collapse completely. Because now you are no longer just changing how reality behaves in the present, you are changing how it behaves in the past. Or at least, it looks that way. And to really understand how far this goes, we need to take this idea out of the lab, out of a small experimental setup, and scale it up to something much bigger, something that stretches across billions of years. Because when you do that, the paradox becomes impossible to ignore. Now imagine this is not happening inside a lab, not over a distance of a few meters, but across the entire universe. Picture a distant object, something incredibly far away, a quasar, a massive source of light, billions of light years from Earth. The light it emits begins its journey long before our planet even formed. It travels across empty space for billions of years, silent, undisturbed, carrying with it a story from the deep past. And somewhere along that journey, it encounters a galaxy, not just any galaxy, a massive one, so massive that its gravity bends space itself. This is called gravitational lensing. Space around the galaxy curves, and light has to follow that curve. It cannot go straight anymore. So when the light from the quasar reaches this galaxy, it has two possible paths. It can go around the left side or around the right side. From our perspective on Earth, this creates something remarkable. We don't see one quasar. We see two identical images, separated slightly in the sky. as if the light split and traveled both paths at once. This is the universe recreating the double-slit experiment on a cosmic scale. The quasar is the source. The galaxy is the barrier with two slits, and Earth is the screen where the result appears. But here's what makes this situation completely different: time. Because after the light passes the galaxy, it doesn't arrive immediately. It keeps traveling for billions of years. That moment when the light had to decide which path to take happened long before anything we know existed. Long before Earth, long before you, long before any observer could possibly interfere. So whatever the light did back then should already be fixed, completely independent of anything we do now. But now imagine this. Tonight, an astronomer points a telescope at that quasar. The light is just arriving right now after billions of years. And at that exact moment, the astronomer has a choice. They can set up the telescope in two different ways. One way allows them to determine which path the light took, left or right. It separates the two images and measures them individually. If they do this, they force the light to behave like a particle. It must have taken one path. The other option is completely different. Instead of separating the paths, they combine them. They use an instrument that merges the incoming light. If the light traveled both paths as a wave, those two paths will interfere, creating a pattern, a signature of wave behavior. So the astronomer chooses, not billions of years ago, not when the light passed the galaxy, but now, in the present. And somehow that choice determines what the light did back then. If they measure the path, it's as if the photon chose one side billions of years ago. If they measure interference, it's as if it traveled both paths all along, the same photon, the same journey, two completely different histories, decided at the last possible moment. And if that doesn't feel impossible yet, it should, because it means something you were never supposed to question might not be real. The idea that the past is already decided may just be an illusion. At this point, you might be thinking this is just a thought experiment, a clever idea, a philosophical trick, something that sounds strange but doesn't actually happen in the real world. But physicists didn't stop at imagination. They built it. In 1999, a team of researchers designed an experiment to test this exact idea in a controlled laboratory, not with quasars, not with galaxies, but with lasers, crystals, and mirrors. And what they found was even more disturbing than the cosmic version. It worked. The setup begins with a single beam of light, a laser. But instead of letting that light travel normally, they send it through a special crystal. When a photon from the laser enters this crystal, something unusual can happen. It can split, not into pieces in the classical sense, but into two new photons, two lower energy particles that are born together at the same moment, from the same origin. These two photons are not independent. They are linked deeply in a way that classical physics cannot explain. This connection is called entanglement, and it means that whatever happens to one of them is connected to the other. No matter how far apart they are, think of them like twins, created together, sharing a single quantum state. The experiment labels them differently. One is called the signal photon. The other is called the idler photon. But they are not truly separate. They are two parts of the same system. Now here's where the design becomes clever. The signal photon takes a very simple path. It travels straight forward and hits a detector almost immediately. This detector acts like the screen in the double-slit experiment. It records where the photon lands. And once it hits, that event is done, recorded, locked in time. The signal photon's journey is over. But the idler photon takes a completely different path. Instead of going straight, it is sent through a complex system of mirrors and beam splitters It bounces, it reflects, it travels a longer route, a delayed route, which means it takes more time to reach its final destination. This delay is everything because it creates a gap in time between the two photons. The signal photon arrives first, the idler photon arrives later. So by the time the idler photon is still moving through the system, its twin has already been detected, already recorded, already part of the past. And yet, the idler photon is about to decide something that will determine how we interpret what already happened. Because along its path, the idler photon will face a choice, not a conscious choice, but a physical one, a branching of possibilities. And depending on which path it takes, it will either reveal information or erase it. And that choice happens after the past has already been written, or at least after we thought it was. Now let's follow the idler photon as it moves through this system, because this is where everything becomes precise, not abstract, not philosophical, physical, measurable. The idler photon enters a network of beam splitters and mirrors. Each component redirects it, splits its path, sends it toward different possible detectors. And at the end of this maze, there are 4 possible outcomes, 4 detectors, labeled D1, D2, D3, and D4. But these detectors are not all the same. They are designed to do 2 very different things, 2 completely opposite types of measurement. If the idler photon ends up at detector D3 or D4, something very specific happens. The path it took is preserved, clear, traceable. If D3 clicks, we know exactly which route it came from. If D4 clicks, we know the other path. The information is intact, nothing is hidden. This is the equivalent of placing a detector at the slits. We are extracting which path information. We are asking the question, where did you go? And the universe gives a definite answer. But the other 2 detectors are different. D1 and D2 are set up in a way that destroys that information. To reach them, the idler photon must pass through a beam splitter that mixes the paths together completely. The paths overlap, interfere, blend into each other. So by the time the photon reaches D1 or D2, there is no way to know where it came from. The information is gone, not hidden, not delayed, erased. This is the key idea behind the quantum eraser. You are not just choosing to observe or not observe. You are choosing whether information about the past exists at all. And this choice happens after the signal photon has already been detected, after its position has already been recorded on the screen, after the event is over. So now we have 2 possibilities. If the idler photon goes to D3 or D4, the path information is preserved. The universe knows which way it went. If it goes to D1 or D2, that information is erased. It no longer exists in any form. And here is the critical point. This choice is not made before the signal photon hits the detector. It is made after. The signal photon arrives first, leaves its mark, becomes part of the past, and only then the idler photon finishes its journey and determines whether the path information exists or not. So the question becomes unavoidable. Does the way the signal photon landed depend on what happens to the idler photon later? Because if it does, then what we thought was already fixed isn't fixed at all. And the past might still be waiting for the future to decide what it means. So the experiment is run. Not once, not a few times, but thousands, millions of times. Photon pairs are created. Signal photons hit the first detector. Idler photons travel the longer path. And everything is recorded. Every single event, every position, every detector click. At first, if you look at the screen where the signal photons land, you see nothing unusual, just a random scatter, a blurry distribution, no pattern, no structure, just noise. And that's important because it means in real time you cannot tell what is happening There is no visible wave pattern, no visible particle pattern, nothing that reveals the outcome, but the real insight comes later, because the scientists don't analyze all the data at once. They sort it, they take every signal photon and group it based on what happened to its idler twin. They separate the data into categories, and this is where everything changes. First, they look at all the signal photons whose idler partners ended up at D3 or D4, the detectors that preserve path information. These are the cases where the universe knows which path was taken. They plot those signal photons on a graph, and the result is exactly what you would expect from particles. No interference, no stripes, just two clumps, as if each photon went through one path, a clear classical pattern. Then they take the other group, the signal photons whose idler twins ended up at D1 or D2, the detectors that erase the path information. In these cases, there is no way to know which route the photon took. The information is gone completely. They plot those signal photons separately. And this time, a pattern appears, not random, not blurry, structured, alternating bands, an interference pattern, the signature of a wave. So now you have two different results from the same experiment, the same setup, the same photons. The only difference is what happened to the idler photon later. If the path information was preserved, the signal photon behaves like a particle. If the information was erased, it behaves like a wave. But remember the timeline. This is the part that breaks everything. The signal photon hit the detector first. Its position was recorded, fixed, done. The idler photon hadn't even reached its detectors yet. The choice of preserving or erasing the information hadn't happened. And yet, when you look back at the data, the pattern of the signal photon matches that future outcome perfectly, as if it already knew what was going to happen, as if it landed in a position that would only make sense once the future measurement was made. This is not a loose correlation. It's exact, precise, consistent every time. The past behavior of the signal photon is tied directly to the future state of the idler photon, and that leads to a conclusion that feels impossible to accept. The past is not independent. It is not fixed at the moment it happens. It is part of a larger system that only becomes fully defined when all measurements are complete, including those that happen later, which means what you thought was already decided may not have been decided at all. At this point, it's almost impossible not to jump to the most obvious conclusion. It feels like we've just discovered a way to influence the past. If what you do later determines what happened earlier, then why not use that? Why not send information backwards in time? Why not encode a message? Change the future by rewriting the past? It sounds like the door to time travel just opened. But this is where the universe closes that door immediately, because no matter how strange this experiment is, it comes with a built-in limit, a rule that cannot be broken. It's called the no signaling principle, and it ensures that even though these correlations exist, you cannot use them to send information backwards in time. To understand why, you have to go back to what you actually see in the experiment. Imagine you are standing there, watching the detector where the signal photons arrive. You're looking at the screen in real time, waiting, hoping to see something, a pattern, stripes, clusters, anything that tells you what's going on. But you won't see anything. Just a blurry mess, a random cloud of dots, no interference pattern, no particle pattern, nothing that reveals the outcome, because all the different possibilities are mixed together, overlapping, canceling each other out. The wave patterns from one group are out of phase with the wave patterns from another. The bright regions of one pattern land on the dark regions of another, and they erase each other. What you're left with is a smooth distribution, featureless, meaningless. The information is there, but it's hidden, completely inaccessible in the present moment. You cannot look at the screen and know what will happen to the idler photon later. You cannot predict whether the path information will be preserved or erased. And more importantly, you cannot control the outcome, because the idler photon's path is fundamentally random. You don't get to choose whether it goes to D1, D2, D3, or D4. The system decides. So even though the past and future are correlated, there is no way to use that correlation to transmit a message. You can't encode information. You can't send signals. You can't cheat causality. The only way to see the pattern is after everything is done. After the idler photon has already been detected, after the future has already happened, only then can you go back to the recorded data and sort it, separate the events, reveal the hidden structures. It's like a locked message. The data is there from the beginning, but the key only arrives later. And without that key, everything looks like noise. So the paradox remains, but it becomes one-sided. You can see the connection after the fact, but you can never use it in advance. You can never act on it, which means the timeline is safe. Cause and effect are preserved, not because reality is simple, but because it hides its complexity until it's too late to exploit. And that leaves us with something even stranger than time travel. Not the ability to change the past, but the realization that the past was never fully defined to begin with. So what does all of this actually mean? Not just for physics, but for reality itself. Because if you follow this all the way through, it forces you to confront something much deeper than particles and experiments. It forces you to question what the past even is. We grow up believing the past is a fixed sequence of events, a timeline that has already unfolded, stored somewhere in the universe like a recording, permanent, unchangeable. But this experiment suggests something very different. The past is not a place. It is not a finished story. It is not a fully written record waiting to be read. It is something else entirely. It is a set of possibilities that only become real when they are measured, when they are connected to the present. The photon doesn't carry a definite history with it as it travels. It carries potential, multiple possible paths, multiple possible behaviors, and only when the full system is observed does one of those possibilities become the story we call the past. This is the idea that divided some of the greatest physicists in history. Einstein refused to accept it. He believed the universe had an objective reality, that things existed with definite properties whether we observed them or not. He famously asked whether the moon exists when no one is looking at it. But Niels Bohr argued the opposite. He believed that properties are not things that exist independently. They are outcomes of interactions, of measurements. And in this experiment, Bohr's view wins. Not philosophically, experimentally. The universe does not behave like a static system with hidden variables waiting to be discovered. It behaves like something that only resolves when a question is asked, when a measurement is made, which means we are not just passive observers. We are participants. The questions we ask define the answers we get. And those answers don't just describe the present. They reach backward and give structure to the past. But here's the final twist. This doesn't mean you can change history. It doesn't mean you can rewrite events or send messages back in time. The underlying data, the raw outcomes, are always consistent. Causality is preserved. What changes is not the past itself, but the way it is defined, the way it is organized. The narrative that emerges when the system is fully measured. The universe is not violating time. It is doing something stranger. It is refusing to commit to a single version of events until it has to, until the full context is known, until all measurements are complete. Only then does reality settle into a consistent story, one that includes both the past and the present as part of the same structure. So when you think about the past now, don't imagine it as something sitting behind you, fixed, immutable. Think of it as something that is still being resolved, still being defined, not because it can change freely, but because it was never fully decided to begin with. The universe is not a recording. It is a process. a continuous act of resolution. And sometimes that resolution reaches backward to complete what you thought was already finished,